Good afternoon, everyone. I'm pleased to introduce to you Alyosha Effels today. He's from CMU, and he's going to talk to us how to do cool things with a lot of images. Alyosha.
Thank you very much, Thomas. I'm very happy to be here. I mean, lunch is amazing, and also it's just great to see so many of my friends here. It's like a big reunion. And thank you very much to Thomas for graciously inviting me and hosting me. So I'm going to, Thomas caught me on my way back from SIGGRAPH, and so the talk is very, very raw and lots of new stuff. So I apologize for, kind of jumping around and not having a very coherent story, but kind of more of a raw core dump of newest stuff. So please forgive me for that. I'll polish it up later for the next talk. So the story is that we want to solve hard problems in vision and graphics, but we don't want to work too hard. And we don't want to actually do all of the hard things that you are supposed to do, kind of AI complete things. So the question is, can we just brute force our way to solving these hard problems? And I think this is a very good place to talk about, brute forcing hard problems. Google is exactly the right audience. So what are hard problems? Well, the main problem, in my view, is that we are robbed of an entire dimension. We have this beautiful 3D world out there, life and smells and sights and sounds and all this amazing three-dimensional reality, and boom, we plop it down onto a two-dimensional plane. Whether it's a painting or the back of a CCD array or the back of your retina, the same thing happens. We basically we lose a dimension. Okay, we lose a lot of the things that were obvious in 3D. And we end up with something like this, where things are not as easy. And then we have the audacity to actually try to reason about this 2D representation in a way that makes sense only if you're in the 3D world. Okay? So we are made our problem particularly hard on ourselves, because we only have 2D representations. And then we want to reason about them in the context of the 3D world that we all know and love. Except, that information is gone. Not only it's not just a hard problem, it's an unsolvable problem, because getting back at the 3D representation from a single 2D projection, you cannot do that, because you can have a bazillion different possible 3D representations that will give you the same projection. Okay, and that's kind of the big vision, the hard vision problem right there. Okay, and in fact, there is nothing you could do if we lived in some kind of an abstract world with pieces of matter kind of floating in midair, right? Then we wouldn't be able to do anything at all. The problem would not be solvable at all. Luckily for us, our world is very structured. Okay, our world is a very small subset of all the possible sci-fi worlds that could have been out there. Our world, has planes, and planes are great things. The fact that you don't have to jump from particle to particle, but actually, can walk on a plane, that's wonderful. And the fact that the plane has a particular orientation because of gravity, it's usually either horizontal or vertical. There are some exceptions, but 99% of the time, horizontal, vertical. There are consistencies in other senses, like illumination. Most of the time, illumination is from above. That's why when you put a flashlight like this, you don't recognize people, because that's not typical. And so there is a lot of things about our world that are peculiar to our world, and that is how we humans can deal with this unsolvable problem of trying to understanding what is it that is being depicted. What is the three-dimensional world, or even a four-dimensional world, because we do also get a sense of time that's being depicted just from this two-dimensional signal. Okay, and the way that that vision researchers approach this is through learning. The idea is that we have our world, we somehow use that as training data, and then we can use it to interpret new data. Okay, and so the classic story that is kind of the understanding of the visual world, the learning and vision slide. This is stolen from Chris Bregler. Is that we have a bunch of training data, we capture it, okay, and then we try to somehow squeeze out all the interesting bits out of it. We try to squeeze out the informative part to model what is it actually represents. And then once we have once we have a model, we can do various things. We can do image understanding. We can synthesize more of this. All of the nice things are available. This is kind of your typical machine learning pipeline. You have lots of data. You squeeze out all the unimportant bits. You only keep the important ones, and then from that you can do lots of things. The problem is that this part is really, really hard. How do you know which ones are the important bits and which ones you can throw away? And this is the heart of the machine learning problem. And it's the whole conferences and careers of people devoted to exactly this step. How do you, understand your data, understand what's important about your data, okay? And there's lots of smart people trying to do that, and I'm not one of them. So I'm going to do something much simpler. I'm going to sidestep the whole problem and do it the Google way. Don't worry about understanding what's important. Just keep around all your training data and do lookup. Okay, that's exactly the Google solution. Looking up the world instead of trying to really reason about it. And it turns out that it has a lot of benefits, not just for text, but I believe for visual data as well. So the Google solution, so I wonder if you guys would take up this claim of mine. I claim that AI is that Google is the AI for the postmodern world. So postmodernism in art is the idea that everything has already been invented, everything has been created. There is nothing new under the sun. And the natural extension for it is that, well, that means you don't have to create anything anymore. You just look it up. Okay, so all questions have already been answered many times in many different ways. And the reason why Google works is just the intelligence is sitting there all over the world on the servers, and you just look it up. Okay, that's kind of the Google story that works so well for you guys. And my main research interest is to see if the same type of power of data could be applied to a much harder case of visual data, okay? And why is it a much harder case? Well, noise is an obvious example, right? So, you might think that your data is noisy, but it's not really. I mean, you have characters, for example, right? You have like ASCII codes for every letter. You have most of the words are really spelled more or less correctly. There is huge amount of noise in visual data. Every pixel is going to be wrong by a lot. Again, high entropy. There is just much more stuff, in an image than in a text, right? The reason why images take up so much space than text is because there is lots of stuff. There is lots of junk as well as lots of signal. And of course, being 2D is also a problematic. The 2D signal is trickier than 1D signal. But yet, we want to see what could we do something in that area, and especially, how much data would we need? Is it possible to do something reasonable with the amount of data that is, obtainable currently and downloadable, and storable at a normal research lab? That is, is it how much do we need? Is it millions? Is it billions? Is it gazillions? Because the problem is so much harder, obviously you need more data. But how much more? Nobody knows. So that's kind of the questions that I'm interested in answering, and I'm going to present a few kind of very raw projects, and I have to mention all my collaborators up front. So I have a wonderful set of graduate students. Derek Hoym, who just got his PhD this morning. Yes. And he's going to UIUC, and he's a really wonderful guy. And James Hayes and Jean-Francois are two of my other graduate students who are been working on part of the stuff I'm going to talk about. And Marcel Ibert is my colleague at CMU, with whom I have also collaborated a lot. And so the CMU gang is great, but I also like to travel. So there is this kind of MIT Oxford gang, Joseph Civic, whom you might have heard of, the video Google guy, Brian Russell, Bill Freeman, and Andrew Sisserman on one of the projects. And then Microsoft Cambridge guys helped out on some graphics project, Carsten Rother, John Wynn, and Antonio Cremonesi. And I'll give references to actual papers later. So I will talk about two parts of this lots of data story. First part is, what if you have labeled data, the easy case, okay? Somehow you got labels, and the somehow is actually thanks to Antonio Cremonesi and Brian Russell, is this label me data set that they are running. And it's essentially people upload photographs, or Antonio uploads photographs, and I gave him a bunch of photos. And then you go in, and before you can download the labels, you have to label a few objects, okay? And so you get this kind of polygonal labels, and you enter a text. So it's very much a kind of a low maintenance vision research endeavor, but they are actually doing pretty well. They're up to something like 160,000 objects right now, and it's becoming a really, really nice data set, and we're very happy that these guys have done it. So what if you have that kind of data? No object classes, people can type in whatever they want, but reasonably good segmentation, okay? So one thing that we could do is we could say this. Well, if we have an image and we have labels, we have labeled people in that image, can you estimate their physical heights, okay? In the world. You have them labeled in the pixels. Can you estimate their physical height? If you have a picture of me, I want to know, how high I am. If somebody wants to buy me a T-shirt, a Google T-shirt, they want to know what size. Okay. Well, it turns out that this problem is pretty simple. If you assume a bunch of things that we have shown before is actually not such a bad assumption. If you assume that really what you want to estimate is you want to estimate the camera parameters relative to the ground plane. So you assume that everyone's on the ground, and basically all you want is you want to estimate the height of the camera and the orientation like this. Okay? Turns out that if you have a bunch of people, and you can go to the National Center for Health Statistics to figure out how tall an average person is, and you have labels which says these are people, it's pretty simple to estimate the orientation of the camera for this particular image. Okay? It's just not that hard. Okay? Well, now we have the camera pose for this one image in this huge label me data set. Okay? Now what? Well, what we could do now is say we have another image which has some people, okay, and some other objects, say cars. Okay? We can use the people to estimate our rough camera parameters, and then we can use the camera parameters to estimate the rough high distribution in the real world of this new class of the cars. Okay? Now that we have this information, we can go further, and we can say, okay, now that we have don't have people, but we have cars, we can use the cars to estimate the orientation, and then we can estimate the orientation of a new class, say a van. Okay? And basically what we do is we do this recursively for the entire data set, and eventually we get to estimate a whole bunch of physical heights of objects and estimate the orientation of the camera for every one of the images. Okay? So this is an example of what we could do now. There are a bunch of people in this image. They are labeled in pixels. And if you put them, on the kind of a lineup, you can see that the people farther away are shorter than the people close up. But with our little trick, which is very simple, we get something that not only estimates the relative height of the people, but actually even gives you their height in meters, okay? And we have done it for a number of classes. And the nice thing is that you can look up what's the standard height of a parking meter or a fire hydrant. And women and men, there are statistics for how high they are. And we're like within 2 millimeters of the correct mean answer. So it's really, it's not that we get it right for every image, but on average, we're actually doing pretty well, okay? And so this is kind of a nice, kind of a data-driven way. It's all very simple. It's a little piece of thing in Derek's thesis, but it shows you that really you don't, if you have a little bit of labeling, a little bit of this labeling can go a long way to kind of go from the world of the 2D image and step up into the world of the 3D scene, okay? And what else we can do with this? I'm not going to talk about it, but this is our CUPR06 work, where we can detect objects, orientation of the geometry of the scene, and the orientation of the camera, and then we can do things like synthesize, top views of scenes. From a single image, we have a overhead view of everything that's on the ground, and then we can even label, where the cars are sitting and where the pedestrians are walking and things like this, okay? And this is again kind of trying to get out from the tyranny of the image and into the space of the scene, okay? Now, what else can we do from a single image? Well, what we can do, we humans, is we can look at this image and we can say roughly what kind of weather it is. We can even estimate, should I wear a jacket or not, and whether I should wear a sun hat or something like this. There is enough information in this image for us to know the rough kind of illumination of the scene. How can we do this for a computer? Well, the way to do it currently in computer graphics is actually the method proposed by Thomas and I's office mate, Paul Debevec, is you take a shiny sphere, a shiny mirror sphere, you place it in your scene, you take a photograph of that, and the shiny sphere basically reflects the entire sphere of light incident at that point. And then you use that for what the graphics people call environment map, and then you can use that information to relight or to estimate the illumination or to even relight objects. But this involves, finding where this picture was taken from. We don't know. This is some Google image photo. And then, traveling there and taking a picture of the shiny ball. But we humans can actually do some of that just from the single image. So what can we do? We propose what we call illumination context. And the idea here is that we are going to approximate the very, very rough illumination of the scene by dividing the image into 3 parts: the ground, stuff that's illuminating from below, the sky, very important for outdoor scenes, and whatever is left, the vertical stuff, okay? And we're going to basically capture some very coarse brightness information from these 3 regions in kind of a very coarse environment map representation, okay? And the way we're going to do this is we're going to use our old geometric context system to estimate the ground, vertical, and sky components of the image, and then we're going to basically just throw it into a color histogram and compute, joint color histogram, and have that as our representation for the image, okay? Now, all the graphics people should yell at me at this point and say, this is all wrong, because environment maps are supposed to be high dynamic range. They're supposed to know exactly how much light you're seeing. And this is 0 to 255. So a photograph has a very limited dynamic range. So this is completely useless for an environment map. But the point here is that we are not using this to relight objects. We are not even using this to estimate anything, really. We're only using this to match, to find other images that have the same illumination, the same weather. And that seems to work actually pretty well. So here are some query images This is kind of, a overcast day. This is a morning, and this is a noonday. And you can see the nearest neighbors using this representation as a query. And you can see that actually the results mostly are quite good, despite all of the shortcuts and all the problems that we have experienced. And one reason for this is basically when you have a lot of data, whatever shortcuts you do in the query image, the same shortcuts would be found somewhere in your data, and you will still be OK. OK, and now here's a very cute application that we did with the Cambridge gang. Say you want to insert objects and images. So it turns out that you can do this in a very simple kind of image-based way. So we don't want to find shiny spheres and take pictures of them, and we don't want to use this kind of a toy clip art example. So what we came up with is we call it photo clip art, something in the middle. Photorealism on one hand, but ease of a clip art library on the other hand. And so the idea is, I'll just kind of sketch it very simply. Instead of saying, I want this car in this scene, go do it, which is it's an impossible problem because the camera orientation is wrong, the illumination is wrong. It's not going to, right? Not good. And I really don't see this as being. I don't think it's possible to solve this problem without solving the full computer vision problem, actually understanding that this is a car and getting the 3D geometry and stuff like this. But we just redefine the problem, and then it becomes much better. We say, we don't want this car. We just want a car. And we have a whole bunch of possible cars. So now our problem is to find out which of those cars would actually look good when pasted into the scene. And this turns out is actually a reasonably doable problem. So the idea is that for every object in the label me dataset, we annotate it with the camera parameters that I talked about, and the illumination context, which I also talked about. And then we basically have kind of the Google model. We have all of our data with annotated parameters. We have our query, which is the image that we want to insert stuff into. And all we do, it's not even automatic. It's basically the front page result of Google. We resort the data and give the user the top matches that we believe, based on the estimates of the geometry illumination here and the estimate of geometry illumination here, we, the computer, believe has a high chance of looking good. Okay? And that's really it. And we have a nice user interface, and then we can get stuff like this. So this is the kind of Abbey Road, improved. So again, there are details of the paper, but then you can really play great tricks on your insurance company and say that you had a horrible accident. Okay, or you can even add traffic to your images, paintings. You can add objects to paintings, and it looks kind of good. This, by the way, big thanks to Google for helping us out. We got this painting, and we forgot to record the URL. And so we didn't know how to ask for permissions. And then Henry graciously did some magic. I don't know what it was, but we got the URL. So thank you very much. We have an acknowledgement to Google, about how Google helped us to find our needle in their haystack. So here's an alley scene, and here's some bunch of American cars. It doesn't look that great, I have to say, but the reason is semantic. You just don't see such huge cars in Europe, okay? Nor parking meters, actually. And this is going to be the new Gates Hall at CMU for those CMUers here. So that's, you have Newell Simon here, Smith Hall here, and this weird thing is going to be the Gates Center. And you can see that this is a rendering that the architects gave us, and they believe that all CMU students look like that. Kind of a shadowy figure. So we thought that this might be a better representation of how lively the campus is going to look like. So that's like one potential application of this stuff. Okay? And of course, sometimes it just doesn't work. And so for example, here, the database just doesn't have enough images of kind of night night with snow scenes, okay? But as you all know, there is no algorithmic problem here. The problem is obvious. You just need to get more data, right? And then things will just, and there's kind of a refrain that a lot of the problems are going to be solved by data, okay? Oh, I'm sorry. Can I say something about the shadows? I can, but after the talk, because I still have lots of stuff. Basically, we do the Google solution to shadows too. We steal the shadow and we transfer it over. That's what we do with the shadows. We detect the shadow, and then we just transfer it over into the new thing. And even if shadows point the wrong direction. So shadows are very important, right? But if you look at Renaissance paintings, you realize that the direction of the shadow is really not important. You can have a window and sun shining through the window, and then the shadow going that way. And nobody notices. So basically, we just steal the shadow from the original place of the object and just stick it in, and nobody cares. So yeah, but I can talk to you later about that. I just want to kind of show lots of little teasers about stuff. So now, what if you have unlabeled data? So you think, okay, now this is going to be horrible. If you don't have any labels, what can you do? But turns out there are some things that you can do. So this is this CMU, MIT, Oxford mega project. And the idea is you have lots and lots of images. Can you discover objects in that huge collection of images? Okay, I'm not going to tell you what an airplane looks like. I'm not going to tell you what a motorbike looks like. I want you to look for the objects and discover repeatable patterns, right? Because in a way, one way to define what an object is some visual pattern that you see over and over and over and over, and then by the time you've seen it for the 100th time, you say, okay, I better think of a name for it. Because it's too much, right? I just need a short name for it, and that's how words come about, right? So this is our definition of a visual object. It's some stuff that's happened so often that you just give up and give it a name, okay? So we want to discover those types of repeated objects in unsupervised way from a huge data set, okay? And the idea here is our approach has two intuitions. So one intuition is this idea of multiple segmentations. So the idea is that all segmentations are wrong. You apply segmentation to an image, and chances are the results will be really bad. But some segments in some segmentations are still useful, okay? And we have shown that with Derek for a previous work, but here it really comes into relief. Here's an image, and here's a bunch of segmentations which we run with different parameters. And you can see that a lot of them are junk, but then there is this one segmentation right here where we get our car as a nice segment, okay? If only we knew that that was the right thing, we would be all set. But at least it's there. At least we got a segment that was good, okay? And this is where intuition 2 comes in. And this intuition is, we have a citation to Tolstoy. We're very proud. All good segments are alike. Each bad segment is bad in a different way, okay? Those who read Anna Karenina should appreciate this, right? The idea is that if you have a segment that is a car, and then you have another image where you happen to segment out a car, that segment and that segment, they should have a lot of things in common. They should be very similar, okay? Whereas if you have a segment that is a bad segment, you have a piece of a car and a piece of a road, it's very unlikely that somewhere else you'll find another segment that will be that same piece of a car and that other same piece of a road. So noise conflicts with each other, whereas signal agrees with each other. And that's the idea. The idea is that the good segments, they should cluster. The good segments should be like each other. The bad segments should not cluster. And that's basically, I just told you the paper. So the idea is we produce lots of segments for each one of our images, and then we basically try to find clusters within that space, that soup of segments. And the tight clusters turn out to be reasonably well segmented objects. And here are some examples. So this is the MSRC data set, and these are some of the clusters that we have automatically discovered. These looks like cars. These looks like some kind of road signs, I guess. This is some fields, I guess. This is sky. This is windows. Those are, I'm not sure, I guess, bicycles with some background. It's not perfect, but you can see that it's actually doing something reasonable. Here's the Caltech data set. And the Caltech data set is really, really simple. So we do pretty well. We get our motorbikes. We get faces. We get a couple of car clusters, I guess, kind of dark cars and light cars. You know, there are some things that just visually don't look the same, but you have to use semantic knowledge. But anyway, this is kind of a first step. And one problem, of course, is that, OK, we're going to use a huge data set. But really, the data sets are all on the order of a few thousand images. So it would be really fun to see what happens if we really let it trip on a huge, huge data set. OK? And now, how much do I have? All right. So now I'm going to tell you kind of the most googliest of my projects that I'm very excited about. This has just been presented at SIGGRAPH. This is a work of James Hayes, one of my students. And nominally, it's a work about filling holes in images, right? But I think there is a larger story. So nominally, the story is that you have this nice European alleyway, and then you have this car that looks just completely out of place. So let's get rid of it, OK? OK, done. OK. Well, not quite, because now we have this stupid hole in the image, and we need to somehow patch it up. Right? So what do we do? Well, the first thing, of course, we run and we go and we implement our old work with Thomas that actually, you know, does a pretty good job. Back in the day, in '99, it does a pretty good job filling in holes in textures or even extrapolating textures. Okay? But if you get something that is non-homogeneous, like a real image that is not really a texture, then you don't get anything. You get basically a mess. And it shouldn't really work, because this is really not a texture. OK? There is a follow-up work by Antonio Cremonesi, who says, well, if you do Efrosin long, but you try to propagate high edge boundaries first, kind of do kind of a little bit of mid-level grouping, and then fill in the rest, then you get better hole filling results, even for real images. But unfortunately, here the hole is still too large. And in fact, it's propagating the frame of the door in the completely the wrong way, right? And some Microsoft product based on that is also not doing too well here, OK? But what's the problem? What's the trouble? The trouble is the semantics. The trouble is that we know that what should be here? It should be some kind of a road, OK? So what if we give up and say, OK, let's ask the user. Let's say, OK, let's query for something that's a road, OK? And there is a couple of recent work which I think are really interesting and exciting on kind of this user-guided image compositing and image search and compositing. And the idea is basically that you sketch of this work, for example, is that you sketch what you want and you put labels. You say, I want road here, I want a car here. And then it goes to a database of labeled stuff. And then it kind of puts together an image for you. OK? So I think it's kind of a very, very interesting user-driven way to solve this problem. But do we really need the human in the loop? Can't we just use the fact that we know what should be here? Why? We know it because the rest of the pixels, the rest of the image, tells us, well, this is kind of building on the left, building on the right, kind of an empty space. Looks like an alleyway. Looks like something like this, right? And in our mind, we say, yeah, this is kind of the scene that is probably here, and here, you have a road. So that's where we get our intuition, from this kind of semantic representation of the image. So now we ask, what we could do is we could say, well, if we could find other examples that share the same semantic structure, building on the left, building on the right, some space in between, then we can go in, we can find the appropriate piece, and we can fix it up, fill in the hole from one of the images sharing the semantic structure. Okay? So that's kind of the idea. But how do we do this? How do we find other alleys like this? Well, we can go to the best search engine in the world and type alley and not get anything useful, unfortunately. And this kind of I feel this is not really, it's not the problem of Google, it's a problem of, an image is worth 1,000 words. So you have to type in 1,000 words to get the image that you want, right? And so instead, why not skip the text part at all and just try to go straight for images? Take a bunch of images, 1,000, 10,000, 1,000,000, 1,000,000,000, and see if we can find good enough matches semantically that would do what we want. And the question is, how many do we need? Is it thousands? Is it millions? Is it billions? Is it even feasible to do this? And the kind of a cool answer, and somewhat unexpected answer for me at least, is that in fact you can. You can do a reasonably good job, this is our result, of finding a reasonably close image and steal the information and fill it in the hole. And I'll just briefly show you our algorithm. So we'll start with a simpler image for illustrative purposes. So this is, I was hiking in the Ligurian coast, and there's this house, blocking the view. So let's get rid of the house. This is going to be the input to our algorithm. Now we want to fill in the hole, okay? So what do? First, we have some kind of a scene descriptor, a coarse representation of what the scene should look like. Basically throwing away all the unimportant stuff and keeping only the essentials. Then we're going to query into our large image collection, okay? From that, we're going to get about 200 best matches. And for each match, we're going to see, okay, does it fit well? Can we align it to fit well into this hole? And then we'll give the user the top 20 image completions, scene completions that our system was able to come up with, and then the user can decide which one they like the best. Okay, so that's the story. So what do? The first, of course, is the data. Data is the most important. Okay, so we got 2.3 million unique images from Flickr, and the nice thing about Flickr is that you get kind of whole scenes. You don't get close-up of objects usually. You get nice big scenes, which is what we really want to work with. And what's 2.3 million? Well, if displayed like this, we'll have to watch an hour to see all of them. So I think I better move on. Now we need to have a descriptor for this image, right? We don't want to query on every single pixel. That's too much, and it's also we don't need to compute all the record all the ripples in the water or all the little houses in the background there. We just want kind of a coarse representation. So what we do is kind of a standard thing to look at the oriented energy at different scales and orientations of this image, and then we coarse it up into a 4x4 grid. And this is, in fact, the scene gist descriptor that Oliver and Teralba proposed back in 2001, of basically capturing very coarse orientation information for the image. And here we are trying to be very careful to make sure that the places where we don't have data, we don't put anything in there so that the missing data part is left blank, okay? Right, like this. And we add to it also some very basic color, a 4x4 color information, just so that we get some color as well. Okay, and then we search. We search our 2.3 million database, and we search it in brute force. Because we have missing dimensions, we can't really do any of these fast speed-up searches. Well, I guess we could, but we tried a bunch of things, and it didn't quite work. So if anyone has any suggestions, we're very welcome. But it's basically not so horrible. We have a bunch of parallel machines, and we just search brute force for nearest neighbors, 200 nearest neighbors. Here is the top 50 or so, and it's nice actually, I think, because you can see that it's getting something that's similar to what we started with, which is kind of almost magical. Okay, and here is, for example, one of the matches. And now we say, okay, now let's do some little local alignment to find the best place where it would fit. So we take the kind of the context, and we do simple searching to find where it would fit best. Okay, and once we do that, we align the two images. Okay, and then we do some graph cut and Poisson blending, basically standard graphic stuff that would blend between those two images in a nice way. And this magic is done, and we get a result like this. Okay? So what we are doing is After that, after we do this for every one of those 200 images, we re-rank the results based on the scene matching distance plus the context matching, the local context matching, plus the cost of the graph cut. Okay? And then we give the user the top 20 results. Okay? And here, there. And again, this is like the first page of results in Google that you can try to pick what you want. And some of them don't really make any sense. And some of them, I mean, a lot of them do what you would expect it to, basically fill stuff with water, which is good, right? Just kind of a little bit boring, but you just fill things with water. Or you have a little bit of the beach here. There are issues, scale issues, yeah. Not quite right, not quite right. This is not a bad one, except it has something stuck in it, and that's what we wanted to get rid of in the first place. So this is the one that I particularly like the best. And notice that you could not do this with kind of a texture synthesis method because, where did those boats come from, right? And in fact, this thing gotten on BBC somehow, and some British guy writes me, I don't understand how you could do this in Photoshop, because where did you get all the boats from? So I said, no, we don't use Photoshop. We use data. OK, so what's the value of kind of giving, instead of giving 20 results to a user, why not just give one? But well, sometimes all of the results are kind of useful. So for example, here is an example. We want to get rid of the road and the bus. And here are some of the results. And you can see that they're really, really different. I'm really not sure which one is, the right one. So here I'll just go through some of the more examples. Here we have an image, and we want to get rid of this facade. Okay? And here is the hole that we filled. And it's another facade. It looks quite good. So let's look at under the hood. And what we see is the matches, the best matches. And you can see that actually just right here it's actually matching a lot of stuff. It's matching kind of vanishing points and the two planes. But notice that it's not really that GIST is so smart. The GIST is just recording little edgelets. You have lots of data. And the data is such that, even on small, very stupid descriptors, you still get some good matches. Okay? So from here, we find this one is to be the best match, and here is where we stole that, and you can see that it's a pretty good semantic match, and there you go, we put it in the hole. Okay? Here is another one. This is James's picture of Lyon, and the crane is not the nice site, so we get rid of the crane, and we fill it in with something nicer. Let's look at the scene matches. Here are the matches, and they look great. And then you look closer, and you realize that actually, like 4 of them don't have water, but have pavement instead, right? But the thing is that even for us, it's hard to tell. So, it does what it's supposed to. It does this kind of a GIST match, a kind of a coarse matching. And this is the best match, and they are really, really close. It's kind of really neat that they're close, and so it's not surprising that you'll fit in very well. Here is another picture from a park near CMU. We want to get rid of these things, and we get a little bit more exciting image. Here, the sky is overexposed, so you can go and shoot another photograph. But who cares? Just get rid of the sky and get some more interesting sky. Here, the hilltop is not looking too exciting. We get rid of that, and we have a new hilltop. Okay. Here you have some development on the beach, but we don't like that in our photo, so we get rid of that, and a pristine beach is resumed. This is a picture from Lyon, and that James took on his holidays, and he was very bummed that the cathedral has the scaffolding, so he wanted to get rid of scaffolding, and this is the result. And we look at it and say, that just looks too good. Something must have gone wrong. What happened? Then we go to see what are the matches. And it's all very nice because most of the matches are nice European cities from above. So it understands the concept of European city somehow. But the best match is this one, which actually is exactly the same vintage point in Lyon, found somewhere on Flickr, just a couple of years earlier before the reconstruction. And it managed to fill in the hole from that image, like so. So this is not what it's supposed to do, right? We're supposed to match semantic scenes, not actually physical scenes. But with more and more data, these kind of lucky accidents are going to happen more and more often. And it's nice where we can use them. OK, so failures. So here is the wacky MIT building, the data center, and we wanted to get rid of this. And this is the best image match. So for such an image match, you can't really expect too much. OK, so for weird scenes, the matches are still not so great. Here is another example where we wanted to get rid of this. And this is kind of, so the two people in the car. And this is kind of shows the fundamental problem of scene completion James likes to talk about, which is that there is really no way to just fill stuff in. You have to synthesize something, right? There is part of a person. You have to hallucinate her legs or do something, right? So it is, in a way, in the end, it is still an AI complete problem. So we'll do much better in kind of filling in holes or in scenes than actual, hallucinating legs and things. OK? So let's see. I have 3 minutes. So we are the first work in this area to actually, see how well we are doing in a somewhat systematic way. So we have an evaluation, a user study. We predefined a data set before we actually did the research of basically a bunch of holes that we want to fill in. And we ran Antonio Cremonesi's algorithm, the closest competitor, our stuff. And we also wanted to keep the original images. Because what we wanted to do is we wanted to ask a person, does it look real or not? All right? So we wanted to see how many of the images would appear real to humans. Now, there's a little bit of a caveat that Antonio's thing produces a single result image, and we are basically picking from the best of 20. So it's not a completely fair comparison. We would have also picked the best of 20, but there is really we tweaked the parameters, and all the results look kind of the same. So it didn't really make that much sense. OK, so the idea is that we don't want the users to see the same image several times because there is a memory effect, and then they'll know where to look. So we get a non-overlapping subset of the image for each user randomly, combine it into a set, and then for every image, we show an image and we say, is this a real image or not? Yes or no, please take your time. We're going to time you, but don't worry, don't hurry up. Just figure out if this is right or not. So is this real? Who thinks it's real? Who thinks it's wrong? Fake. Real? Fake? Oh, you guys are good. It is, in fact, fake. This is the real image. And these are the results. So if you go to the very right, this is time, response time of the people, and this is how many of images they labeled fake. So the rightmost column, the rightmost area is the first result, and basically, we basically fool people 30% of the time. Okay, 30% of the time, people believe that our stuff is actually real, compared to 10% of the time for Cremonesi. Okay, so that's good. So we're a pretty good jump from previous work. But notice that at that regime, a whole 14% of real photographs were also marked as fake. So it seems that the people are kind of trigger happy and oversensitive, and the reason is because we told them that there will be fake photos. So they're suspecting something. They're not naive users anymore. They're suspecting, and so they really kind of overshot. So one way to kind of try to compensate for that is to say, well, let's consider what happens at the first 10 seconds. They really didn't have a chance to really scrutinize every pixel in the image and just kind of glance at it like you'll glance at a bunch of trashy magazines at the checkout counter, not really looking at it carefully. And here you see that virtually no real images are labeled as fake, which is good. But at this point in time, even though Cremonesi's stuff is already 70% has been thrown out as fake, for our stuff, about a third are fake. So 2/3 of images, people are still, it's not clear that they're fake. And so this kind of gives us hope that seems like we are in fact doing something reasonable. Definitely not all the way there, but it seems like things are moving in the right direction. So why does this work? And I think this is kind of interesting for you guys, especially is it the just descriptor? Is it the particular features we picked? Is it the particular graph cut implementation that we used with our particular fitness function? Well, I believe that it's none of the above. I believe that it's basically just data. Okay. So we first started with a small data set, and it really didn't work. And here is why. Here is an input image, and here are 10 nearest neighbors from a data set of 20,000 images. And none of those nearest neighbors are particularly near, right? They're really not that close to the query, okay? And you really need to work really hard, do some kind of a semantic processing to really figure out similar images. Whereas if you just increase your data set a couple of orders of magnitude, suddenly your nearest neighbors, in whatever space you do, even something as simple as SSD would probably work similar, you get a number of really, really good results. Okay? So it's just that as you have more and more data, the actual distance metric stops being important or becomes less important. In the limit, if you have all the images in the world, you don't care what your distance metric is, because you will be always finding the exact match anyway. It's like the cameras of the future will just have a link, internet link. You take a picture, or even better, it will have a GPS. You take a picture, it will record where the picture is taken from, and go to Flickr and just feed you the image that should have been there at that location, right? If you already have all the data. So it's kind of this argument. So the more data we have, and it seems like, it's, OK, I'm sorry, this is 2.3 million images, sorry, not 23. Yeah, 2.3 million images. It seems like, 2.3 million, that's nothing, right, for you guys. That's really nothing. And yet, we're already starting to get pretty good matches. So I think that's really the stuff that's work, and that's really the stuff that's exciting. OK, and there is a parallel paper to ours, the concurrent work of Antonio Taralba, Rob Ferguson, Bill Freeman, which has actually explored this in much more detail. A really, really cool work called Tiny Images. What they did is they collected 70 million tiny 32 by 32 images, and they are seeing exactly the same behavior. As you get more and more images, things just become nicer and simpler and more powerful. So do read this paper. It's a really, really nice paper, technical report. So the big picture is that, if we can have an input image, given an input image, if we can find reasonably close matches from a database, even without labels, then lots of cool things could be done. Yes, we could fill in holes in the images, but that's kind of a little graphics application for fun. But we can do cool things too. We can transfer labels that might be there. We can transfer semantic information. We can transfer timestamp information, or weather information, or geographic information, tons of things, and really kind of get at the concept of brute forcing image understanding. Instead of understanding it, just find close enough examples and steal them. And that's I think the big plan for the future. And I think that it's going to be quite doable, I believe at least. So thank you very much. Any questions? So I don't see very well, so just shout.
Mode with a person that is being turned into a flower pot or whatever it was, and you need this understanding in order to be able to fill holes about the surrounding around the hole. Have you done any work on that in that regard?
Like a local surroundings.
Yeah, or trying to find images using your very same technique to try to use that knowledge in a way.
So we do this local stuff as a post process, right? I don't think that matching locally directly is going to do very well, because you first need to get the global context right, because all the local stuff looks like all the other local stuff. The same, my button here would look like a wheel of a SUV, and will look like a cookie from the cafeteria, and will look like 1,000 other things. And it's really only the big picture that will disambiguate between them. So I very strongly believe in the power of using the global stuff for kind of initial matching. And then after you kind of got yourself into the right groove, then you can try to kind of dig deeper and get some local information too.
Because you will always get objects that are smaller in scope and are local to the boundary condition.
Yeah, but I think if you just do the local matching, you'll just get something that looks nothing like your query image at all. And I mean, the problem is that for small objects, we'll never have enough data. That's just not going to happen, right? Even in this tons and tons of, even if you take all the images in Google, you will still not have enough data for small objects. So this is really only kind of the image understanding from afar, not really a local thing. For a local thing, you still have to do the real computer vision stuff, mid-level grouping, segmentation, recognition, all that stuff, I think. Other questions?
You have quite a bunch of clustered items, like motorcycles.
Mm-hmm.
Doesn't it seem natural to take the closest elements, the core of the clusters, and turn them into morphable models?
Yes. I mean, that certainly makes sense. It's not super easy because we still don't have correspondence. Right? We just have this is a motorcycle, this is a motorcycle. For a nice morphable model, you need a correspondence. But yeah, that makes a lot of sense. I would love to see more morphable model stuff being done on large data sets. For example, you guys have all these phase detectors running, and why not collect all those faces and build a huge active appearance model of a million faces? I think this is exactly the right strategy to pursue. The biggest morphable models that have been built, to my knowledge, is basically 1,000 things, 1,000 faces. And I think there are more people in the world than there are faces. I think by an order of magnitude. There are 5 billion people, but maybe only 5 million different faces. So it's really we get 5 million faces and that's it. We can model everyone. I think it's cool. Yeah. So, but I agree with you. For things like motorbikes, for 3D objects like cars, it becomes harder because then you have to take viewpoint into account and other things. But I think it would be kind of a cool thing to kind of build in models from scratch automatically. Kind of crawl the web and build in graphics models. Yeah, I think that would be great.
One more.
Yeah.
In the graph you showed, the comparison of your CM. Do you have any sense of how the blue curve will move if you increase the number of images or decrease the number of images?
Oh, it would get better, of course. Of course. No, if you increase the number, so if you decrease the number of images, it just kind of slumps. Antonio Torralba kind of has in his graphs kind of a gentle slope. As you slowly increase the data, you get better and better and better. Our experience has been actually more dramatic. But it's also less quantified. We just kind of anecdotally noticed that there was just nothing, and boom, million images, and it just worked. And so that kind of was very satisfying that it was data was looking out for us. It was somehow helping us from the background. But yeah, more data I think would really improve it. Whether it's going to be another jump or not, I don't know. It might. Torralba claims that there is some kind of a saturation at some, well, not saturation, but basically you get the slope becomes small enough that you need to do something more clever. But I think this is a really, really interesting research direction that, yeah, we just don't know how much data is good.
Last time to speak again.
Thank you.
Thank you.